having seen how to obtain the transfer matrix for an optical system, let's take a look at what the components of these matrices, the elements in the matrices, mean. And it's really an interpretation of, for a general optical system, then we can obtain a single 2 by 2 matrix called the ABCD matrix that has really everything we need to know about the optical system. So let's take a look at a few special cases. And first case to look at is the case when D is equal to 0. If it happens that D is equal to 0, then what can we say about this system? And if you look at it, we'll have A, B, C. I assume the others are not 0 at this point. And I can get the output, the input transformed by this matrix M, where D is equal to 0, into the output. And I'll use yi and theta I for the input values of the system of array, and then y0 and theta 0 for the output. What we have is something like this. We probably have an optical instrument of some sort in here, and then usually we would put our input plane some point in front of it, and our output plane somewhere in the back. So our real system matrix goes from the input plane to the output plane. And so oftentimes we might have a translation to get to the really instrument here, and then another translation matrix to get to the final point. But the interesting thing about the case when the element D is in the ABCD matrix is 0 is this last term, theta naught, then is just C y naught. So if we get that equal to 0, and here I've got yi, that's the height above the optical axis at the input plane. And it doesn't matter really what that height is, or, well, it matters, I guess, what the height is, but I have anything coming out of that at all different angles. Then the output angle, so long as I'm at a point from that same height, yi, the output angle, so yi is the same, then the theta naught at the output plane, so what comes out, are all rays that have exactly the same theta naught. So this ray that comes at 1 theta naught comes at this point, this one maybe comes out of here, this one maybe comes out here. And so we have an input plane, an object on the input plane, getting rays in all directions, but they emerge at exactly the same angle, and it doesn't matter what the angle theta is. There's no theta I over here because 0 times theta I was 0. Now we've got a name for that. We know that for this optical system that goes from the input plane to the output plane, that if I find a point over here on this side in which all the rays emerge parallel, well, that's the primary focal point, or the primary focal plane in this case, because it could be any point along this input plane. And so so by setting setting D equal to 0 here, then we are able to locate the primary focal point, which we've been calling F1. Any rays emanating from a primary focal point or an object that's in the primary focal plane emerge parallel, all at the same angle. Well, let's take a look a little further. Now let's take a look at the case where A is equal to 0. And again, if you multiply A times this matrix here, you'll get AYI times B theta I. But if A is 0, I just get B theta I here. And that's what we have here. I get A times YI, B theta I. Again, I've got some optical instruments in here. I've got an input plane and I've got an output plane. And this is kind of interesting because it says that no matter uh, no matter what my point is along this input plane, so no matter what yi is, since A vanished, there is no yi, no y input, and no matter what the height is, every ray that comes from this plane at the same angle, so theta I for these parallel rays are coming at the same angle, by the time it gets to the output plane, they're all going to come from the same y naught, from the same height. And if you remember, what that amounts to is if you have a parallel light incident on an optical instrument, you get they'll all go through the secondary focal point. So if A is equal to 0, that can help us locate the secondary focal point of the system. If B is equal to 0, so now we're up here, B is equal to 0, then I get Y naught Y output is equal to A times Y input. The B term, the theta term, goes out. And so in this particular case, if B is equal to 0, then B term goes out. I get Y output is equal to A Y input. And that's kind of interesting because it says if I have a point, P here, that's at a height yi above, that no matter what angle the rays come from on this, by the time they arrive at the output, they're all going to have the same height. Because the input yi is the same coming from this point P, so they're all the same. Doesn't matter what the angle is, but all these rays are going to come and go through the point P prime, really the image point of the point P over here. It's all at the height y naught, all at the input height yi. And again, the optical system is this everything in between. I've got optical element here. I may have a translation and a translation here between the output and the input and the output plane. But having this, then I can certainly take the ratio of the image height to the object height. And in this case, the object height is yi, and the image height is y0. And I know that y0 is AYI. The y output is equal to A times y input. So the yi's go out, and I get that the lateral magnification is A. So if B is equal to 0, then the matrix element A gives us the lateral magnification of an object. The last one is similar. Now I'm going to have C is equal to 0. And again, we're looking at the ABCD matrix. So if C is equal to 0, then when I multiply it out, I'll just get that theta naught is equal to D times theta I. And this is sort of the angular equivalent. So C is equal to 0. In general, theta naught is CYI plus D theta I. But if C vanishes, then I get that theta I times D is theta output. Well, if I look at that, what that says is that if I have parallel light coming in here, they'll all at the same angle, theta I, they're parallel, they all make the same angle with the optical axis. Then they will be output over here. If theta I is the same for all of these rays, then they'll all be output, even though they have different yi's over here. They'll be emitted at different heights here as well. But the angle theta naught that the output ray makes with the optical axis is all the same. So parallel rays in, parallel rays out, but the angles may be different. And in fact, I can get the angular magnification, we've been calling that big M, is the output angle, theta naught, over the input angle, theta I. And we know that the input angle is theta I, and the output angle is d theta I, so the theta I goes out, and we get that the angular magnification is d. So when C is equal to 0, d will give us the angular magnification. Well, you really, that describes the meaning, I guess, of each one of the elements and when they vanish and what that means. But to really see how to use these, we need to work through a few examples, and we'll proceed to that